Hello and welcome to this walkthrough presentation of Part B-1 of the New York State Chemistry Regents exam given August 2015. Explanations will be highlighted using graphics from the Prentice Hall Brief Review by Patrick Cavanaugh, 2016 edition. In this presentation we're going to start with question 31. Which conclusion was drawn from the results of the gold foil experiment? Recall that the gold foil experiment was one of many of the early studies that helped us understand the structure of the atom. In this experiment, Ernest Rutherford and his team fired alpha particles through gold foil, and they tracked the scattering pattern of the alpha particles as they traversed through the gold foil. Rutherford and his team observed that the majority of the particles seemed to pass through the gold foil undisturbed, suggesting that the atoms in the gold were made primarily of empty space. The scatter pattern that was observed by those particles that didn't go straight through led the team to conclude that the gold foil had these dense areas that had positive charge because of the way they repelled the positively charged alpha particles. He dubbed these concentrated areas of mass in the gold atoms the nucleus. So we go back to our potential choices and we pick out the major conclusions drawn from the result of this gold foil experiment. And they were that the atom is made of mostly empty space, answer number 2, as well as the fact that the nucleus is a positively charged dense core of mass within the atom. And none of these answers confirm that. This one refers to them as negatively charged, which is wrong. The electrons really weren't discussed much, but they were thought to be orbiting the nucleus. And number 1 here, the atom is electrically neutral. No, that was not one of the conclusions of this study. The primary conclusion was that the atom is mostly empty space. Question number 32. Which electron configuration represents an atom of magnesium in an excited state? To help us with this, we're going to go to the periodic table and look at the box that contains information for magnesium. And we know that the bottom part of these boxes give us the electron arrangement. In magnesium, we have 2 electrons in the first energy level, 8 in the second, and 2 in the third, when the magnesium is in the ground state. So to be an excited state atom, we have to still have 12 electrons, but they can't be in the ground state order of 2, 8, and 2. We have to look for a representation that has that spread out a little bit more. There could be many possibilities. So we go back to our potential answers, and the first thing we're going to do is count to see if we have actually 12 electrons represented. Answer 1 does have 12. We have 7 plus 3, 10 plus the 2. The second response here, I see 15 electrons, so that can't be it. Number 3 has the correct number of 12. And number 4, we're looking at 15 electrons again. So 2 and 4 are out. Now, representation 3 is the actual electron configuration of the ground state. So you can see in answer number 1, we've taken one of the electrons from the second energy level and promoted it to the third energy level. This is an excited state representation of the magnesium atom. So our answer is 1. Question 33. Which group on the periodic table has elements with atoms that tend not to bond with atoms of other elements? These would be the noble gases that you've heard so much about. And they are members of group 18 on the periodic table. This is a very basic question. We like questions like this in the Regents because they should be like doing layups. Question number 34. Which group on the periodic table has at least one element in each of the 3 phases of matter at standard temperature and pressure? Let's bring up the periodic table and take a quick survey. And this will be very helpful information for you to remember as you go into the Regents exam. On the periodic table, there are primarily solid materials. Most of these elements are solids. There are only 2 liquids at room temperature. Let's highlight the liquids in green. Our 2 liquids include mercury down here and bromine over here. There are several gases on the periodic table, and it's helpful to just remember which ones they are. Once you have that, you'll have the whole picture. So let's fill them in. Hydrogen is a gas. All of the noble gases, of course, are gases. There they are. And then there are only a couple of other gases on the periodic table. They include this little wedge right here, this little angle: nitrogen, oxygen, fluorine, chlorine. Once you've highlighted those, just keep in mind that the rest are all solids. So this question is asking us to find one column where we have all 3 phases of matter, and you can see pretty clearly that's going to be column number 17. Let's just zoom in on column 17 for a moment. we have these four elements included here. Gases are your fluorine and chlorine, both gases. Bromine is the only liquid on the periodic table, other than mercury, but it's in the column 17. And iodine is actually a solid at room temperature. So there's a column with all three phases represented. And it is column number 17. So we're going to select answer number 3 for question 34. Question 35. Rubidium and cesium have similar chemical properties because, in the ground state, the atoms of both elements each have what? We have 4 choices to choose from here. 1 electron in the outermost shell, 2 electrons outermost shell, 1 neutron in the nucleus, or 2 neutrons in the nucleus. Well, let's take a look at these 2 elements in the periodic table. Here's rubidium and cesium. They live one right on top of the other. They're in the same column together. They obviously have way more than 1 neutron in their nucleus because they're number 37 and 55. They have at least 37 and 55 neutrons. So answers 3 and 4 are silly. Now, as far as their valence electrons go, the outermost energy level has but 1 electron. And that's recorded right here in the electron configuration of each one. So our correct answer is going to be 1 electron in the outermost shell, answer number 1. Question number 36. As the first 5 elements in group 15 are considered in order of increasing atomic number, that would be from top to bottom in the group, the first ionization energy does what? Increase, decrease, decrease, then increase, or increase, then decrease? Well, the only way to really get this answer is to look up those numbers, or if you happen to remember, the pattern on the periodic table is that ionization energy generally decreases as you go from top to bottom through a group. But let's look more closely. I've looked up those values from table S, which you could easily do, and written them in for column number 15 with nitrogen at 1402, phosphorus 1012, arsenic 944, antimony 831, bismuth 703. And these are all in kilojoules per mole. So obviously the first ionization energy decreases as you go from top to bottom with increasing atomic number. So we're going to select the decrease, answer number 1, and we move on. Question 37. Which substance in the table below has the strongest intermolecular forces? This table is giving us the substances and their boiling points data. Now, if we have strong intermolecular forces, it's going to be very difficult for us to boil the substance. So all we have to do here is pick the substance with the highest boiling point. That'll be the substance with the strongest intermolecular forces. So we compare the 4 values in the chart. We pick out the highest one, the 293, that's associated with hydrogen fluoride, and that will be our choice, number 1. Question 38. Which ion in the ground state has the same electron configuration as an atom of argon in the ground state? To help with this question, we'll take first a close look at argon. Argon's electron configuration in the ground state is signified by 288, so it has 2 electrons in the first level, 8 in the second, 8 in the third. Now, if we consider the 4 possible choices here of aluminum, potassium, oxygen, fluorine, let's take a look at their ground state configurations, which are given to us from the periodic table, and I've recorded those here for you. Now let's change those to their ionic configurations. If aluminum is +3, as suggested by the answers, we'd be losing these 3 electrons here, and the new configuration would be 2-8. Oxygen is a -2, means we're going to gain 2 electrons, so we'd add those here. We'd get a configuration of 2-8. Potassium as a +1 means we would lose 1 electron right there. So potassium's ground state configuration of 2881 would become the ionic configuration 288. You can see that that matches, so potassium is going to be our choice. And just to be complete, if fluorine were to gain 1 electron, its new configuration would be 2-8. So our correct answer is going to be the potassium +1 ion, answer number 3. Question 39. What is the number of pairs of electrons shared in a molecule of N2? To form a molecule of N2, we have to put 2 nitrogen atoms together, and we have to have them share their electrons in the valence shell. Well, they each have 5 electrons in their valence shell. In order for them to simulate 8 electrons, they're going to have to actually share 3 electrons each. So, if you recall, the Lewis dot structure for this is going to have a triple bond between the 2 nitrogens. So we have 5 electrons donated by this nitrogen, 5 by this nitrogen, and 3 bonds between the 2. A triple bond means that you have 3 pairs of electrons being shared in the triple bond. So our answer to this question is also 3. Question number 40. Which statement explains why a carbon to oxygen bond is more polar than a fluorine to oxygen bond? Hopefully you understand that we can check this by looking at electronegativity differences. But let's analyze the answers anyway and pull in some data from table S to help us with this. The first statement, at STP carbon has a greater density than fluorine. This is probably true because carbon's a solid and fluorine is a gas at STP. But this has not much to do with the strength of the bond. So it's an irrelevant statement. A carbon atom has more valence electrons than a fluorine atom. Actually not true. Carbon has 4, fluorine has 7, so that's a false statement. The difference in electronegativity between carbon and oxygen is greater than that between fluorine and oxygen. Let's test this out. Here's the 4 elements in question, or 3 elements, carbon, oxygen, and fluorine. Electronegativity differences you can see between the carbon and oxygen is pretty big. It's about 0.9. Difference between the fluorine and the oxygen is only a 0.5. So that is our correct answer. And we'll come back here and circle number 3 and put that up as our answer. But just to make sure, number 4, the difference in first ionization energy between carbon and oxygen is greater than that between fluorine and oxygen. This actually is not true. The difference between the carbon and oxygen is not going to be quite as great as the difference between the other two. So answer 4 is also a false statement. We're going to stick with answer 3. Question 41. A mixture consists of sand and an aqueous salt solution. Which procedure can be used to separate the sand, the salt, and the water from each other? Well, in this mixture, the salt is dissolved in the water, but the sand is insoluble, so it's not dissolved. So the first thing we're going to do is remove the sand from the other two by filtration. So we're going to start with filtration to remove the sand. And then if you heat it up, the water will evaporate and the salt will be left behind. So the answer is number 4. Question 42. An aqueous solution has a mass of 490 grams and it contains 8.5 times 10 to the negative third grams of calcium ions. The concentration of the calcium ions in this solution is, you can see from the answers they want us to calculate in parts per million. So we go to table T, we bring up the formula for parts per million, here it is, and we plug in what we know. The mass of the solute, that's the calcium ions, was given to us as 8.5 times 10 to the negative third, that goes on the top. And then the total mass of the solution of 490 grams goes on the bottom. You divide that and multiply by 1 million to get parts per million. Your answer will come out to 17 parts per million. So that's going to be answer number 3, a computation problem. Question 43. A sample of hydrogen gas is at 2 atmospheres, that's a pressure, and 273 K temperature, occupies a volume of 5 liters. Volume. The gas sample is completely transferred to a 10-liter sealed rigid container. That's going to be a new volume, so a V2. What is the new pressure of the gas sample when the temperature returns to 273 K? This is a combined gas law problem. So we're going to go to table T and get our combined gas law formula. P1 V1 over T1 equals P2 V2 over T2. And we're just going to plug in the values. Hunting for the values in the question, we see we were given a starting pressure P1, a starting temperature, T1, a starting volume, V1, and we have a new volume, V2. We're asked to find P2, so that is the item in question. And you can see our temperature 2 was given to us as well, and it matches the original temperature, so temperature is not a factor here. Temperature stays the same. I've set up the computation as a combined gas law problem over here, where P1 and V1 is 2 times 5, and the P2 V2 is P2 times 10, and the temperatures cancel out because they are the same. So 2 times 5 is 10, divide both sides by 10, 10 divided by 10 is going to be 1. So the answer to our problem is 1 atmosphere when we solve for P2 in the expression. Answer 1. Question 44. Given the equation for a system at equilibrium, and we have nitrogen and hydrogen being added together to produce ammonia, and energy is given off in the equation, and you can see it's an equilibrium system with dual arrows. If only the concentration of nitrogen is increased, what will happen to the concentration of, and they give us 4 different choices of what could happen here. So let's analyze the whole thing. If you increase the concentration of the nitrogen by adding more, we recall from Le Chatelier's principle that when the concentration increases, the system will rid itself of what was added. So in other words, if the concentration is added, we're going to move the reaction away from what was added in order to dispose of it. So this will enhance the forward reaction. So we expect to see more ammonia. We expect to see less hydrogen. And we also should see the temperature rise in the system since we're going to produce more energy. Let's check our answers, see which one works. Ammonia increases. Yes, that does happen. Ammonia remains the same. No. Hydrogen increases. No, it decreases. Hydrogen remains the same. No, our answer is number 1. Le Chatelier's principle helps us figure out that the ammonia is going to increase as a result of adding more nitrogen to the system. Question 45. A hydrocarbon molecule has 7 carbon atoms in a straight chain, and there's a double bond between the 3rd carbon and the 4th carbon in the chain. What is the official name, a UPAC name for this hydrocarbon? I've drawn the structure over here, and when we're going to name this structure, the first feature that we really obviously see is that there is a double bond. So double bonded hydrocarbons are members of the alkene series, so we know the name is going to end with ENE. That eliminates 2 answers. Now, since we have 7 carbons, the prefix for 7 is hept. All the answers say that, so that doesn't help us. But now, what do we do with this numbering system? Well, if we locate the double bond on the left side of this chain, it's in actually the 3rd position. So the proper name for this is 3-heptene. Now you might argue, well, couldn't we also close the 4th position? If we count from the right side, we'd have 1, 2, 3, 4. So it's actually in the 4th position if you come from the right. Well, the rules of the International Union of Pure and Applied Chemists tell us to use the lowest number possible. So we have to orient this molecule so the double bond is in the 3rd position. That's the better name. The answer is number 3. Question 46. Given the balanced equation representing a reaction, here's a organic reaction where we're taking a 2-carbon molecule, we add fluorine to it. You can see the fluorine has attached itself to the structure and the double bond has been broken and there are no other products. So, which type of reaction is represented by this equation? Let's throw away fermentation because there's no alcohol involved here. Let's throw away polymerization because that involves joining together multiple repeated units of the same thing, and we're not doing that. We have a carbon compound and fluorine. They are not the same thing. So are we adding or substituting? I'm going to go with addition here because we've taken the fluorine and literally added it to the molecule without taking anything out of the molecule. We broke the double bond to do that. That's an addition reaction. Had this been substitution, we might still have the double bond and some of the hydrogen would have been eliminated. But we didn't eliminate anybody. We just added fluorine to the structure. So it's answer number 1. Question 47. Given the diagram representing an incomplete electrochemical cell, solid copper will be deposited on one of the carbon electrodes when the wires are connected to what? Well, you can see that the entire vessel is open. There's no separation from the electrodes. Both electrodes are made of the same material, and there's only one solution here. So the only way anything is going to happen in this system is if we supply energy to make it happen. So this is an electrolytic cell. We need to attach a battery to the system, number 2. Just connecting the wires to each other won't do anything, and we would connect them using a switch. So 1 and 3 are actually the same answer. And having a voltmeter would measure if something was happening, but it's not going to make anything happen. So the best answer is number 2 for the electrolytic cell. Question 48. What is the volume of 0.3 molar sodium hydroxide needed to completely neutralize 15.0 milliliters of 0.8 molar hydrochloric acid? This is a typical neutralization problem, which is done in a titration experiment. So we're going to go to table T, bring in the formula for calculating such things. MAVA equals MBVB, and this is what all those things mean. You should recall all that. And we're going to plug in the numbers from the question, so let's highlight them first. The volume of the 0.3 molar sodium hydroxide, that's your base, so that's what we're looking for, is the volume of the base, and they've given us the molarity of the base. That's this value here, 0.3, and we're going to neutralize 15 milliliters, that's a volume of the acid, and we have the concentration of the acid is 0.8, so that's going to be the molarity of the acid. Putting these values into the equation, we wind up with 0.8 times 15 equals 0.3 times the volume of our base. So 0.3 times the volume of the base is equal to 12. Dividing both sides by 0.3 gives us the volume of our base as 40. And the unit is milliliters. That's going to be answer number 4. Question 49. Which equation represents a spontaneous transmutation? This is a nuclear chemistry question. We're looking for a spontaneous transmutation which involves either an alpha, a beta, or a positron being emitted from the nucleus of an atom. The first two equations have nothing to do with nuclear chemistry. The first one happens to be a single replacement reaction. The second one is a decomposition reaction in standard chemistry. Our third equation is certainly nuclear, but it's not spontaneous because we're actually adding two particles together. So we're smashing neutrons into a plutonium in order to cause a nuclear reaction to occur. And yeah, there's a beta particle given off, but not spontaneously. This is artificial transmutation because we had to add the neutrons. So that's not the right answer. The correct answer is number 4. We have a calcium atom undergoing positron decay and producing the daughter product of a potassium-19. So we have answer number 4. That is your natural transmutation that occurs spontaneously. And question number 50. Which particle has 2 neutrons? We have 4 particles represented in the answers here. Let's analyze them. Well, answer number 1 is a neutron. So a neutron doesn't have 2 neutrons. It is a neutron. Answer number 2 is a hydrogen atom. If the mass is 1 and it has an atomic number of 1, 1 minus 1 equals 0. This has no neutrons, so that's not the right answer. Our third response has a mass of 2 and it has an atomic number of 1, so to get the neutrons we subtract the atomic number from the mass. 2 minus 1 equals 1. That is not our answer either. And finally, our correct answer number 4, we look at the atomic mass minus the atomic number. 4 minus 2 equals 2. That meets the criteria of this question. So the particle with 2 neutrons is the helium particle, answer number 4. And that concludes this section of the August 2015 Regents exam, part B-1. You want to look for the other parts on the YouTube channel or go to the website at alchemtutor.com. If you have any questions or comments or would like to get permission to use any of this material, please contact me at asnyder@alchemtutor.com. Thanks for watching. I hope you found this video useful.